Okay, so today what we'll get to grips with is using the quadratic law of resistance for drag forces. So you can see I put this at the top here. Okay, I'll underline this. This is what we looked at in previous lectures. And basically it says if we have a object moving with the speed v here through some resistive medium, then sometimes you can experience a drag force which has the magnitude equal to this b times v squared. Okay, so in other words, the force you experience is proportional to your velocity squared. And this is normally associated with resistive media that have high Reynolds numbers. So this is now explored through this example below, related to a parachutist. Okay, it says parachutist falls from a plane and experiences a drag force due to falling through the air. Okay, quite naturally. Now we're told that it turns out this drag force acts according to the quadratic law of resistance, and an initial velocity for the parachutist is 0. Okay, then we're asked to just find the speed. That's what we need, the speed of the parachutist. Okay, so as usual, what we're going to do is start off with the diagram. I'm going to attempt to draw a plane as best as possible. Okay, there we go. There's a little door for the parachutist. Parachutist falls. The parachutist has very long arms in this case, in comparison with the plane. And okay, and probably we need another wing just for the sake of sanity on the other side. Okay, so this is the picture. I'm going to call this our reference point O, where the plane is. And let's take, for instance, positive direction to be downwards. So this is Y. Okay. So the motion of our parachutist is this. Motion is downwards. So what we have from this diagram is we can start to label some forces which are going on. We can start to put together the forces. So now write down forces experienced by parachutists. Now remember, these forces have to be written in terms of vectors. That's what Newton's equation of motion is asking you for. What's the vector that describes the force acting? So we have a little aside diagram that we'll do this with. Here's our parachutist. Of course, before he didn't have the parachute. Now he's got a parachute. So what have we got? Well, the usual mg term, gravity force. And there I wrote the magnitude. Please keep this in mind. If you're unsure what I'm talking about, please consult other videos. And then we have the drag force, which has the magnitude bv squared. Okay. Or even better. So v is the speed. Well, because we have v square, we'll have v lowercase square, and here v is velocity of parachutist downwards. And I can construct a vector using this v to describe its velocity, the velocity of the parachutist. So we have v underscore, as usual for vectors, is v of t, j. Because my motion is assumed to take place in y direction. Motion assumed to take place in y direction, downwards, in fact. So in other words, this guy is going to be positive. Well, okay, we don't need to actually prescribe this. It doesn't affect actually what we're going to do. We don't really need to say something about the sign, but whether the speed or velocity is positive or negative. Okay, so drag force, we need a vector for this. So we need Fd, and the gravity force will have Fg. When we calculate these two, we will then sum them up and put them into Newton's second law. So Fg. Well, Fg is the force due to gravity. We know its magnitude is mg. We know it acts vertically downwards, so we need J. Now, is it positive or negative, the sign in front? Well, force acts in the direction of positive y, so it's plus. Fd, drag force, is then, well, what? As magnitude bv squared. Remember that this thing, this b is positive. Then we have J, y, again, drag force always opposes the motion. Remember from a couple of lectures ago, we said that if you have an object moving with some speed v in a particular direction, that drag force is the force that opposes this motion. So you can see that the force opposes our motion. It has magnitude bv squared. So the force acts in the direction of negative y, which is opposing the positive direction of our axes, y, which is downwards, so I need minus. Okay, perfect. Now, Newton's equation of motion then says m dv by dt is F. F is resultant force. How do you get the resultant force? Well, this word resultant is the link with the vector. Resultant of a vector of a collection of vectors. It just means sum up the vectors you know. So in this case, if I sub in what I know, I get mg minus bv squared j. Good. So now, if I just take this across, I'm going to continue to substitute in what I know. So I know that my v, for instance, is now v times j. V underscore is v times j, so this goes there. So if I compare left with right, of course, simple rule from vector, from the analysis of vectors gives you this. We get the differential equation, m dv by dt, mg minus bv squared. All right, now, actually, how it turns out is, what happens is you've actually met this before. You've met an equation similar to this. So we have an equation for unknown velocity v. And we've been told the initial condition for v. It's a first order ODE. First order differential equation. So we need an initial condition. So we know that initially the velocity is 0. That's our initial condition. And you've actually met this. So where did you meet it? Well, you met a similar equation when we looked at stability and population dynamics. We have seen this before when reviewing stability of differential equations, diff equations. That's a bit naughty because we also did difference equations. So if I just expand that a bit, differential equations and stability. So we solve something like this, and that's what we're going to do today. All right then, so that's 1, that's 2. Now solve 1. Okay, now 1 we will try to solve for the general solution to the equation. Remember that this is the solution that embeds constants of integration, and we'll just get those constants from applying the initial conditions. Okay, so now how we do this is we treat like any other separable equation, because that's what it is at the end of the day. The right hand side can be written as a product of some function times a function of v. Okay, so some function of t times a function of v, and that function of t happens to be constant. So what I'm going to do is I'm going to just do some pre-manipulation before we do this. I'm going to take out the factor minus b because I like to have my v's with positive coefficients in this. So we have this. All right. Then I'm going to divide both sides by m. And I'll go a step further and divide both sides by v squared minus mg over b. Good. So rearranging gives this. And then we just integrate with respect to t. So I integrate 1 over v squared minus mg over b, dv by dt equals integral minus b over m dt. Of course, minus b over m is just a constant. So now I'm going to go and do some straightforward things with this integral. And then we'll talk about what we need to do with the left-hand side. So, of course, right-hand side is now this. So, in fact, get rid of that. That's bad style. So, minus b over m t plus an arbitrary constant of integration gives me left-hand side. Why? This is constant. This is a constant, so we can write that. This is an arbitrary constant of integration. Now, so we have now this equation to deal with. By the way, standard stuff again, this part is just dv by chain rule. How many times have we done that? Probably sick of doing it by now. But it's interesting how all the problems we've looked at always use this kind of approach. Okie doke. So that's our problem. Now we've converted everything to this. We'll deal with this constant in a bit. So I have this to do now. Looks impenetrable because we normally have linear factors in the denominator. Actually, well, there is something we can do, and you've seen this before. So to tackle this, to do this, write function as in terms of its partial fractions. Okay, so now there's a bit of legwork to do. Okay, so you can see that we know. So I'm going to call this 3 and we'll come back to it. So we know that 1 over v squared minus mg v is equal to 1 over the difference of the product of two terms. Okay, so we treat the denominator as the difference of two squares. Sorry, I said that wrong. The denominator is the difference of two squares, so we can write this as the factors. Okay, you can check this for yourself. It's pretty standard. And knowing this, we have now two linear factors in the denominator. Hence, fractions, no, that doesn't even make sense, factors. Okay, hence, therefore, we can write this as this. Right, so A and B, we should determine. Perfect. So that's our problem now. Let me just copy this down here. Right. Okay. So how do we determine it? Well, clearly the right-hand side is this. Now I showed you can go the whole hog, and what you can do is you can write down this combined fraction on the right-hand side and compare left with right and solve two algebraic equations. But for simplicity's sake, what I'm going to do is I'm going to select values of v that will simplify our job and allow us to find these coefficients. All right, okay, so here, this is what we've got. We've got this. And if we, of course, the denominators in these, the expressions that I'm highlighting now, and that we'll use on the next page, the denominator is, of course, the on the right, the product of those two linear factors gives me the denominator on the left-hand side. So I'm not going to bother rewriting this, but comparing numerators. What we have is the equation, like this. And so, as I said, you can expand, compare coefficients of what's on the left with what's on the right. But instead, let's choose value. Choose v to equal square root m g over b. And this gets rid of b term. And what we end up with is this equation 2 square root mg over b, a equals 1. So a, quite nice, is 1/2 square root b over mg. All right, next, choose, I want to get rid of the a term, so easily I can do this by just choosing v to be this. And then what happens is I get minus 2 square root mg over b times capital B equals 1. So b is minus 1/2 square root of b over mg. Brilliant. So now, therefore, what we have is now exactly what we need, because we can integrate the linear factors. We have this. We have this left-hand side, 1 over v squared minus mg over b is this. Just a second, I have to remind myself what the original expression was. So v minus m, v minus. Yeah. Okay, v minus, and then I have the square root at this in the denominator. Perfect. And then I have this term, so I have to insert b, which is minus 1/2. Okay, now I can do some more simplification for sure, because I have a common factor. Now I have a common factor of common factor of 1/2 square root b over mg. But all right, it's not necessary, but it's up to you. Okay, so return to 3. And we'll sub this in. So if I return to 3, this is what we have. Okay, this is what we have. And I'll now plug in the left-hand side exactly this expression. So now we have this. I'll just put the results there. We know that the fraction inside the integral on the left-hand side is also this. And this gives us a chance to integrate some linear factors. So, integral, we have on the left integral of 1/2. Oh, don't forget to put this in front. Integral. Okay. Minus 1/2 square root b over mg integral equals minus b over m t plus c. That's what it is now. Okay, quite easily then we can integrate on the left hand side, so we have 1/2. And now I'm going to take out this common factor. It's pretty pointless to keep it in both terms. So I have ln, the modulus, square root in general, of this. And then I'm subtracting ln, modulus of this, v plus the square root of mg over b equals minus this. Okay, then I can combine this. So I have 1/2 square root b mg ln. Now one big modulus, using the law of logs and properties of absolute value function. Then I have this. I have the following. Okay, so now rearrange for v. Rearrange for v. And what do we... So how are we going to do this? Well, first I'll divide by the obvious factor on the left-hand side. Let's just write this. Now, here I will have 2. I will have 2 square root. I'll have a minus in front as well, don't forget. So what will I get? Well, I have square root b m. Sorry, that's wrong. Square root m, and in the numerator, sorry. So I'll have square root of bg over m. That's it. T plus now I'll put c2. C2 is just equal to c multiplied by twice the square root of mg over b. Okay. That's all it is. So it's an arbitrary constant. I don't really care too much for this. And well, that's just how it is. All right then. So next, exponent of both sides. As you can see, all this is pretty standard now. As they say, it's all academic from here on in. So I have e minus 2 square root bg over mt, and then ec2. This will just be another constant in a second. So, of course, I have absolute value on the left-hand side, so then I can write this. Being naughty, I swapped the sign for some reason. So I have this. Okay. equals A. And let's say A0. Constant A0. And then this exponent. Right, where A0 is, and I'm going to stop explaining what the constants are in a second. This is plus or minus EC2. Right, now we've got this to rearrange. Can we do it? Absolutely. This is straightforward. So this then just implies I have V minus square root of mg over b equals A0. Get rid of that. E times minus, e to the power of minus 2 bg over mt, now times this factor. And what else? Well, now I can multiply out on the right hand side and have things involving v on the left and things not involving v on the right. So I have this v. I'm going to skip a few steps, hope you don't mind. So I just multiply out the brackets on the right hand side and then rearrange to have v on everything in v on the left and then everything without v on the right. So okay, common factor then on the right is this, and I have this. Okay, so then v is just this, square root mg over b multiplied by 1 minus, sorry, now that's completely wrong, a0, e minus 2, e to the power of minus 2, square root vg over m times t plus 1 minus a0 multiplied by this exponential. Great. Okay, so if I haven't made any mistakes, then we should be able to now get the constant. So now find a0, now find a0 with initial condition. V of 0 equals 0. So this gives us this equation. Perfect. Okay. It's a pain in the neck to write this out. Probably there's a quicker way. So of course, in the denominator, now, just a second, this is positive, so I can get rid of this, so I have this. Additionally, we have zeros in the exponents, so I have a0 plus 1 over 1 minus a0. So this just tells me, if I rearrange, just multiply by 1 minus a0, it just tells me a0 equals minus 1. So with this, v of t, so v of t is equal to this. V of t is equal to the following. We have v of t is equal to square root mg over b. And now I just insert the constants. So I have e minus 2 square root bg over mt. I did promise that a0 was minus 1. So let's put the 1 first. How about that? So I have this. And I'm subtracting it in the numerator, 1, for this term from 1. So I have that. And then in the denominator, I have 1 plus. Okay, now, I could leave us there, but I just want to show you something. This can be simplified further. So, just a second. So this is done. So this is great. This is great. What we need to do now is just, I'll show you a quick simplification of this. So using material from, so get some practice with using the conversion of hyperbolic to exponential functions from this module, calculus. What we get is the following. So I take this, and what I'll do is I'll take out a factor. Take factor e minus square root bg over mt in numerator and denominator. And what you'll see is the following. You'll see this now gives, so this is equals, it gives you this. Of course, if I take the same factor in the top and the bottom, I don't need to worry about having an extra factor in front because I've taken the same term out. I have the ratio of these factors and they just cancel. So I have this minus e with this power over, and you might actually recognize this now as the following. So remember that sine hyperbolic of x is the following: e x minus e minus x over 2 cosh. Hyperbolic in terms of exponentials is this. And so tanh, or tan hyperbolic, is then the ratio of these two functions, which is just then the ratio of the following. My definition for cosh is wrong. Sorry. It's this. Okay, so you can see this is actually in our formula. Now, with the x replaced by square root bg over m times t. So v of t is now this. Tanh. I call it tanh, tan hyperbolic. And you have the following: square root bg t. All right. And that's it. Okay, so what does it mean? Final thing. So, I mean, from a personal perspective, unless I'm told otherwise, I would accept this answer. This is a nice condensed form. Nice condensed form. Now remember that this tan hyperbolic tends to 1 as t tends to infinity. And also you can see that from the above expression as well, that this ratio will tend to 1. But basically what's going on is the following. If I plot the graph of this, v, there's time on the bottom. Then when v is 0, of course, tan hyperbolic is 0. And then you just get this type of curve. Something like this. Probably less aggressively steep. Probably something like this, if you can draw. All right, and you are because this tan hyperbolic tends to 1. What you're eventually tending to is this, which is your terminal velocity. Okay, so that was how you solve a problem involving the quadratic law of resistance. Hope it's been useful. See you next time.